Hi, welcome to StatStuff. I'm Matt Hansen. This lesson is part of an extended series on hypothesis testing in the analyze phase. In this lesson, I'll review the two proportions test that's used when comparing a proportional type of metric to itself across different time periods, locations, or groups. I'll spend the first part of this lesson reviewing some of the critical concepts that can help you to understand how to use this test. But despite that, I recommend that you at least review the prior lessons on hypothesis testing if you haven't already done so. But for now, let's review again why we even need hypothesis testing.
Well, we need hypothesis testing because, remember, our goal for the project is to resolve the problem by first building a transfer function. We don't want to just alleviate the symptoms that we're seeing, but we want to get to the root cause. You may recall my example of my daughter Hannah. We don't want to just alleviate the arthritis pain that she was feeling in her leg, but we want to heal the root cause, which was the strep throat. So if we don't know what the root cause is, then that means we need to build a transfer function to figure that out. By building the transfer function, we can know what changes, that is, what improvements that we need to make that should fix that root cause. Now, if you recall, the transfer function is defined as y equals f of x. That is, the output response of y is a function of one or more input x's. It's part of the IPO flow model, again, that we described before in the IPO flow model, where we have an input that leads to a process and an output. Well, the y refers to that output. The process piece refers to the function that's applied to an x, the x being the inputs that are part of it. So it's really expressed in the IPO flow model to an equation. Now, how does this transfer function fit with hypothesis testing? Well, hypothesis testing tells us which of those x's, which of those inputs that we're looking at, are independently influencing the y, the output metric. When we reject a null hypothesis, we're building evidence proving which x's are guilty of driving the y. And what we'll do at the end is we'll compile all the evidence in the improve phase of DMAIC, and that's when we'll begin to fix those root causes or come up with a plan that's going to fix those root causes. Now that we know from the hypothesis testing which of the x's are the most critical x's that have the most influence and where we need to make the biggest changes that are going to affect our output y.
Okay, now let's review again the various steps that we follow when doing hypothesis testing.
On a high level, the steps begin with a four-step process, which was starting with a practical problem. We're stating the problem as a yes or no question, and then we want to convert that problem into a statistical problem. That's going to help us to figure out which is the right statistical tool or method we're going to use to help figure out how we're going to do the analysis. And then we apply that statistical tool or concept on it, and then we interpret the results from that and come up with some analytical answer. And then from that, we would interpret the analytical answer into some practical solution or some practical way in applying that so it would make sense to us. And at the heart of doing the hypothesis testing, again, for steps 2 or 3, that's where we drill down to 6 additional sub-processes or sub-steps in order to figure that out. So it started off with defining the objective. Then we want to state the null and the alternative hypotheses. Then we define the confidence level and the power levels based off of the alpha and beta risks that were identified. Collect the sample data, and we want to calculate the p-value. All these are part of building this statistical problem. And then once we've done that and run the test, then we interpret the results. This is going to be the point where we decide whether we're going to accept or reject the null hypothesis. This is what we'd follow when we want to go through the formal hypothesis testing.
All right, now let's review again the chart for finding the right statistical test and where the two proportions test fits into all this.
Well, in this drill down we've seen before about finding the right statistical test, what we're going to be looking at is the two proportions test that falls on the left-hand side under the section for proportions. Again, this is because the values that we're going to be looking at are both discrete type of values. And because of that, and because of looking at proportions among those discrete values and doing a comparison between one value and another value that are similar to each other, we're going to be using this particular test called the two proportion test.
Okay, before we dive into this test, let's review again what I mean by proportions.
Well, proportions are measurements with using discrete values, and they're generally going to be represented as a percentage. So even though they are percentages and percentages are numeric, they're not to be confused as continuous values. So just be careful. There could be some risks if you're using percentages or measures of proportion for some tests that are really designed to be used only for continuous values. So just be aware of that risk that might be there. Now, defects and defectives are the measurements we might use for measurements of proportion. So as an example here, we have 5 different units, and each of these dots represent an opportunity per unit, and the red dots represent a defect that might be within each unit. Well, based off of from a unit perspective, we might say, well, 4 of these 5 units are a defect because they have at least one of these opportunities that's a defect. So in that case, the DPMO measurement we might use is 800,000 or 80% defective. Or however, we might say from a defective perspective, that is, how defective is each unit, and if there's 9 opportunities, in this case there's 2 defects. In this next unit there's 3 defects, and so on. From a defective perspective, how defective each one is, we might say the DPU is 1.8 based off of the total number of opportunities and the number of defects we have, or it's 20% defective. Now, why are statistical tests needed for proportions? Well, simple proportions using percentages, they might be insufficient. If you're just comparing a percent to another percent, that may not be complete. You have to really account for the level of confidence that you can have in those percentages, because you may not be able to trust the raw numbers. So as an example, you might have 50% proportion of 100,000 records. Well, that's going to be very different in the implication than if you have 50% of only 100 records. So you have to account for the difference in the sample size, which could affect the overall proportion, which ultimately affects the precision of the proportion that's represented.
All right, now we can dive into actually showing how to run the 2 proportions test in Minitab.
Well, for the 2 proportions test, when are we going to use it? Well, it's when we want to compare one proportional value with another proportional value so that we can determine if there's a statistical difference between the 2 values. So if you're going to be using it within Minitab, you would go to the Stat menu, select Basic Statistics, and select the 2 proportions in the menu. And then what you're going to see when you open that up is you're going to see this type of dialog box. It doesn't necessarily require having these inputs actually within columns. If you have them columns within the worksheet, then you can select those over here, but you don't have to in this particular type of test. You can also just type the values directly into the dialog box itself. So what we have here first of all is each row is represented for the items that are being compared. So for the first item that you're going to be comparing is going to be on the first row, and the second item on the second row here. And then what's going to be represented here under the events for each of the first and second rows are the number of errors or defects or whatever the portion is that you're going to be measuring and comparing between the 2 groups. And then the trials represents the total number of samples for those events for each of those things you're going to be comparing. So what you're comparing in this sense here is there are 82 particular events like defects or 82 non-defects out of the 130 that were going to be compared to the proportion down here of 94 defects, 94 events among the 130 there. So the portion is 82 of the 130 out of 94 out of the 130. You're trying to compare the difference. Is there a statistical difference between the 82 and the 94, since they both have about, in this example, the same number of trials? Now, the number of samples can be different between them, and that's okay. In this example, it happens to be the same, but it doesn't have to be every time. And you can have this options button that's selected as well. By clicking on that, this is where you can define in here the confidence level, and you can also select in here the alternative in the sense of defining how the test is going to compare the 2 different proportions. So when you click OK and run these, then it will give you the result to tell you the p-value of whether the level of risk of determining whether there is a statistical difference between these compared values.
Now let's walk through a couple examples of the 2 proportions test. First, we'll start with an example where we're measuring repeat calls at a call center.
This example is going to be looking at repeat call activity between 2 different call centers. So as a background information for this, let's say that we got a call center in Phoenix and another one at Reno that handles different types of call activity from the customers. But the goal for both of those call centers is that they want to reduce the repeat calls within 2 days. That is, if a customer called in at this moment, they want to see how many of those customers actually called within 2 days from this moment. And by not calling back within the next 2 days, we're assuming their call was actually resolved. So we want to reduce those number of repeat calls within that 2-day time frame. So there was 130 samples of calls that were taken from each of those locations, and for Phoenix there were 82 that found to have no repeat call activity, 82 that were good, and there were 94 from Reno that were good because they had no repeat calls from the customer. Well, the practical problem we want to ask ourselves is there a statistical difference in the repeat calls between the call centers? Well, on the surface, it looks like Reno is performing better because 94 out of their samples were good. That is, they had no repeat calls. And 94 seems to be much higher than Phoenix at 82. So on the surface, based off of the sample, it looks like Reno is performing much better. But what we want to figure out is there a statistical difference. Is Reno statistically different and better than Phoenix? So what we want to do is then convert the practical problem to a statistical problem. We'll start off by stating the null and alternative hypotheses, where the null hypothesis is that we're assuming no difference. They're both innocent. There is no difference between both locations and the proportions between both locations. Where the alternative, we're saying that there is a difference between them. They're not equal to each other. We're also going to accept the traditional or default value for the alpha risk and beta risk, where our confidence level is going to be 95% and power level is going to be 90%. And then for actually typing the statistical problem into Minitab, what we're going to do is go to the Stat menu, select Basic Statistics, and choose the Two Proportions option. From within the dialog box that shows up, what you're going to select is the Summarize Data portion, because we're just going to plug these values directly in. We're not going to have to type them into a separate worksheet and reference them from within Minitab. So instead, we're going to type these values in the Events column. We're going to type in 82 at the first one, and then 94 like we showed in the prior slide. And then in the next column, under the Trial section, we're going to put in 130 for both of them, because there were 130 samples from each of those locations. 82 is for Phoenix, and 94 that we typed in is for Reno. And then we're also going to select the Options button, where it's going to open a new dialog box. We're going to make sure you have 95 selected as the confidence level, and then you're going to have the alternative defined as not equal. So when we run this, click OK, we're going to get this type of output as our statistical solution. So what does this mean? How do we interpret this information? First thing we want to do in this output is look at the p-value that comes out of it. In this case, we've got p-value at a 0.11, which means there's 11% risk of being wrong if we claim a difference between these values. So since that p-value is greater than our alpha risk, greater than the 0.05 that we defined earlier, then we fail to reject the null hypothesis. By saying we're failing to reject it, we're also saying that we are going to accept the null hypothesis, which means we're stating this, that we're going to accept this, that the Phoenix proportion is equal to the Reno proportion. There doesn't seem to be any statistical difference between the two of them. Even though on the surface it looks like there's a clear difference between an 82 and 94, however, statistically this is proving there's 11% chance being wrong if we were to claim that they were different. But we're only willing to accept the 5% risk of being wrong. So this is more risk they're willing to accept, then we have no choice but to fail to reject the null hypothesis. Again, that means we're accepting the null hypothesis that there's really the same proportions between the two locations. Also, you can look at the 95% CI, which stands for the confidence interval, for the difference. And if we see that those reflect the lower and upper bounds of the confidence interval, and if we see that it spans across 0, then there's less difference between the compared values. So from a practical perspective, what we're saying is that the sample that we have, the 130 from each of those locations, is not sufficient to prove a statistical difference in the repeat call activity between Phoenix and Reno call centers. So what you could do, though, is if you were to increase your sample size, there may truly be a difference between them, but the sample size that you have is insufficient to prove a statistical difference. So you probably, if you think there really is a difference, you have to go back, collect more samples, enough that you can statistically prove there is a difference between the two call centers.
Now we'll walk through another example in using this test when measuring billing quality.
Well, in this example, we're going to be looking at the billing quality between two different billing locations. So for the background, we'll say that there's a billing department that has a goal of trying to reach 98% accuracy for its customers' bills. The billing information that's entered is either going to be done at Chicago or Miami. So we had a sample of about 1,000 bills from each of those locations, and by looking at the two locations, there were 17 errors that were found for Chicago and 28 errors that were found for Miami. So from a practical problem, we want to ask ourselves, is there a statistical difference in the billing quality between the billing locations? Well, again, for 98% accuracy out of the 1,000 samples, that means if we had 17 errors here, that means there was 983 or 98.3% accuracy rate, which is exceeding the goal that we have for 98% accuracy. For Miami, we take the 1,000 minus the 28, and we're saying that there's 972 that were successful, or 97.2% accuracy rate. Well, that is less than the 98% accuracy goal that we have. So it would look on the surface, based off of the 1,000 bills that were looked at, that Chicago is performing better. They're achieving their goal, and Miami is not. However, we still need to ask ourselves, is there a statistical difference, despite it looking on the surface, based off of the sample, that there's clearly a difference between them, that Miami is failing to meet the goal and Chicago is meeting it? We want to find out statistically if there really is a difference between these two locations. So we need to translate this to to a statistical problem. So we're going to find out the null and alternative hypothesis, and what we're going to say for the null hypothesis is that the Chicago portion is equal to the Miami proportion. That is, they're both equal to each other. There is no difference. However, the alternative, we're going to say that Chicago is not equal to Miami's proportion. So there is a difference between the two locations. For the confidence level and power levels, we're going to accept the same 95% confidence and 90% power. And then for this statistical problem that we're going to type in a mini tab, we're going to go again to the stat menu, select basic statistics, and select the two proportions option. Under the summarize data option, what we're going to do under the events column is select 17 and 28 respectively in that column, and then for the trials column we're going to type in 1,000 because there are 1,000 samples taken at each location, or 1,000 trials that were run at each location. We're going to select the options button, and for the confidence level you want to make sure it says 95 since that's what we defined earlier, and for the alternative again it's going to reflect not equal since that's what we defined earlier, that we're saying the alternative is that the proportions between Chicago and Miami are not equal. So for the statistical solution, it's going to create this kind of output like we've seen before that goes into the session window within Minitab, and we interpret it the same way. We look for the p-value. In this case, the p-value is 0.097. So we're willing to accept 5% risk, up to 5% risk. But in this case, since our p-value is 9.7% risk, that's more risk than we're willing to accept. So in this case, again, we fail to reject the null hypothesis. By failing to reject the null hypothesis, then we presume innocence. That is, we presume that Chicago's proportion is equal to the Miami proportion. And so that means there is no statistical difference between the two values that we're comparing. They're actually performing about the same based off of the samples that we have. So what does the p-value of 0.097 really mean in terms of risk? Well, again, when we compare to the alpha, we can clearly say, well, we're going to have to fail to reject the null hypothesis, or again, we're going to accept it. But that's the amount of risk that there really is, 9.7% risk. So we have to compare this now to our power level. Because our power level, our beta value that we use to determine the power level is 10%, then we're going to look at that as the 10% risk that we're willing to accept. And this is now a value that shows up between 5% our alpha risk and 10% our beta risk. Because it falls between there, that means there is a chance that maybe there is something going on. There's clearly not enough data to prove that there is a difference between Chicago and Miami, because my percent of risk reflected in the p-value is greater than my alpha risk. But because this p-value of 0.097 is less than my beta risk, there is a chance there could be something going on, but I might actually be missing it. So I have to be careful. So in this case, it does not exceed my beta risk, and because of that, I need to just be cautious that maybe there's more I need to research. Maybe I need to collect more samples or do something different, because I'm very close to my beta risk threshold that I'm willing to accept. So from a practical standpoint, what it really means is the sample doesn't prove. The 1,000 sample bills that we have from each location is not enough to prove a statistical difference in the billing quality between both Chicago and Miami. However, we can be 90% confident there is a difference. That's like taking the 1 minus the p-value. So that's really close. And again, because it's so close to our beta risk that we have, what we might want to do to change the results is actually collect more samples. If there should be a clear difference between them, and because we haven't reached our beta risk threshold of 10%, we're just really close to it, there could be something going on. We might actually have something that's guilty, but we just don't have enough data to fully convict it, and we don't want to let it go free and acquit this suspect that we have before us, because there is still some strong evidence it could be guilty, just not strong enough to fully convict it. So we might need to go back and collect more evidence. In this case, that means going back to collect more samples, rerunning the test, so we can actually prove if there is a statistical difference between these two locations we're comparing.
Now I'd like to show you a template that I built in Excel where you can apply this two proportions test in a really dynamic way.
Now what I want to show you is how you can run the same type of two proportions test from within Excel instead of actually using Minitab. Because I don't know if you noticed, but it can be kind of cumbersome to have to retype the values over and over again. And if you don't have access to Minitab, it's not a default value or function that's available within Excel, but there is an option that I built that allows us to run this in Excel if we wanted to. So on the website you should see a link for looking for the proportions test.xlsb file that I built to help run this, and I'll show you how that works. Now, in order to run this from within Excel, you're going to need Excel at least 2010 or higher. Otherwise, you're going to get some errors that may not function as designed because it requires some additional functions that are only available in at least Excel 2010 or higher. So the template that I built for this is actually in two different sections. The first section is going to be a simple two proportions test in Excel. And what this is designed to do is just do a real quick test, that same kind of test you would actually run with the Minitab. So it's really similar in the language and the layout that you would have in Minitab, but again, it's allowing you to run it from within Excel. This is what that section looks like. It's towards the top of the form. So in here, it's using the same language, where you have trials and events, and you have a sample 1 and a sample 2. Now it's a little bit reversed from the layout that we had from within Minitab, but at least the language is still the same. Trials here is going to be reflecting the values, like the number of samples that you're collecting, and the events are the portion that you're trying to compare of those trials. So you just plug in those values, and by plugging those in, it's automatically going to calculate for you the p-value. This is the same p-value you're going to look for like we already ran from within the Excel, within the Minitab file itself. So if you wanted to plug in the numbers here, you can do that and you get the same result as if you're running it in Minitab. Pretty straightforward. It gives you some additional options in here that might help, but the p-value is really what you're going to look for, and you interpret it in the same way. In this example that's showing here, when you want to compare the proportions for these values that are being compared, the p-value comes out at 5.5%. So again, if you're looking at a 5% alpha risk, then it's insufficient. It's really close to that level of risk. So normally you might say you fail to reject the null hypothesis. But the fact that it falls between the alpha and beta risks, then you have strong evidence to prove it could be guilty, just not enough to truly convict it. It's not beyond that threshold of reasonable doubt. So you might want to go back and collect more samples and more data just to push it over the edge, so you can have more confidence that you're really got enough data and evidence to prove there is a statistical difference between the groups that you're comparing. Well, this is what the simple portion looks like from within Excel. Again, pretty straightforward in comparison to what we've seen in Minitab. But what I want to show you instead is the dynamic portion, which is going to be a lot more effective, because the challenge is you may not want to have, if you're getting a report from a system, you have a whole bunch of things that you want to compare. It's going to be very cumbersome to have to type it in for each of these to calculate the p-value and type in every one of these things that you're comparing. That's a lot of typing to do it. So there's an easier way I've created using this dynamic two proportions test within Excel. And it looks a little bit like this, where all you have to do is copy and paste some simple values, and you can run it automatically on tons of values simultaneously. Pretty straightforward. So the way I'll explain how it's laid out is, let's just say you have some sample data that might look something like this. Now we might have, in this case, this is comparing values from day after day. It doesn't have to be like this. This is just for this example. What's most critical in this particular test when you want to run it, what's most critical is that you have this column, where the column represents what you have up here as the number of trials. And that's the portion that you want to reflect in here as well in this column. Immediately to the right of that, you have some sort of metric value. That metric represents the portion. Or up here, we didn't reflect it as a percent, but it's truly represented as a proportion. It's something smaller, a portion of the total number of trials. So what's most critical for this test to run is that you have one column designating the total number of samples, and immediately to the right of it, you have some metric value representing the proportion. So again, this is really similar to a lot of reports that we might normally get, where you're comparing for the first day, here's the number of samples you've collected, and here's some metric. And you compare that to the next day and the number of samples and then some metric. Or you can have other things that you're comparing. Again, this column is where it says call date is not as critical. It's just some unique identifiers so you can distinguish between row and row within here. But this column is not as critical. What is most critical to run this, again, is this survey volume column and the column to the right of it called metric percent. So once you have some values like that, then what you can do is copy and paste these next two columns where it represents the absolute difference and p-value. So I'll try to explain is what these mean. The absolute difference column is merely a calculation of the absolute raw difference between one row and the row previous to it. So in this example, we've got 84.88%. Subtract from that 86.73%, and the raw difference between these two rows is reflected here as a negative 1.86%. And then the next row here is comparing 85.93, subtract from that 84.88, and the raw difference is 1.05%. So all this absolute difference column at first is the numbers that's reflected here is merely the raw difference from row to row, from the current row and the difference between that and the prior row. And it's doing that for each of these values and putting that raw absolute difference. Now what it's also calculating in here, here's the heart of the two proportions test, where it creates this p-value column. This is the actual p-value, so it's comparing the sample and portions that are in this row with the next row. The raw difference comes out to a negative 1.86% difference between them. Is it statistically different? Well, according to this p-value, it's at 0.001. Well, if we're using 0.05 as an alpha risk, then there is a clear statistical difference between this row representing January 2nd and the row before it representing January 1st. So, because the p-value is below 5%, what this also does is reflect this cell as red. So that way red stands out as something that is where you have some failure, or where the p-value is below 5%. Now, if it's above 5%, like these others much lower here, if it's above significantly greater in the p-value that's reflected here, then it's not going to be red. It's still going to reflect the absolute difference, but it's not going to be red, because what you're concluding here is there's no statistical difference. For example, if we look at the last one, it declined 0.63% from January 5th to January 6th. The raw difference is the negative 0.63%. But there's a 30% p-value, or 30% risk of being wrong. So that's why this is not colored at all, simply because there's not enough data to prove a statistical difference. Now, what you might have noticed here is we've got this orange or yellow type of highlight. That is when your p-value falls between 5% and 10%, assuming 10% is your beta risk. So if your p-value falls between the alpha and beta risk, then what you're basically saying is this is where the core problem is. You don't have enough data that clearly convicts it, like in this first example, to clearly prove beyond a reasonable doubt that there's a difference between the two values being compared. And you don't have you can't say that you can clearly show that it's innocent either. You haven't reached your 5% threshold, but you're beyond your 90% power level. So you're within that 5 and 10% level of risk, and because of that, you don't have enough to prove it's guilty, but you do have enough to say it could be guilty. So that's when it highlights here as yellow, or this orangish type of color, where this is where it's most critical. You can clearly say there's a difference from January to January 2nd, but January 2nd to January 3rd, I might need to go back and get some more data. Because I may not be as confident. It's above my 5% risk, but because it hasn't reached my 10% beta risk threshold, there could be something going on. So I may need to take a different action on that. So it's really where this comes in. Again, all you have to merely do is, as long as you have your data set up in one column, the number of surveys or number of samples, the column next to it you have the proportion. Then all you have to do is literally copy and paste the values in these two columns that are circled in here, paste those immediately next to the other two columns, and it'll automatically calculate that for you. And it'll do it instantly. You can copy and paste that all the way down across all of your values. Now you'll notice in the original test too, when you download the file, there's this representation that we're seeing where it's comparing one row to the row beneath it, but there's also a variation of it where there's another dynamic layout, and that is it's comparing within the same row. So instead of comparing one row to the next row, it'll have one row with a value for a survey and proportion for one group, and immediately to the right of it on the same row it'll have another group value looking like this, another survey and a proportion. And again, it's going to have your same two columns here, the absolute difference in the p-value. It works the same, where if you have your data set up in that format, you merely have to copy and paste these last two columns, and it'll calculate for you what the p-value is, what the raw difference is, as well as highlight in red or in yellow. Now, if you need to change the values because you have a different level of alpha risk or beta risk, then you can dig into the formulas to make those adjustments for the conditional formatting if you want. But since by default there typically are going to be 5% alpha risk and 10% beta risk, the default is used here. So you can always change that in the conditional formatting within Excel if you want to highlight them based off of different p-values that come out of the result.
All right, before we close this lesson, let's discuss how we can apply some of these concepts in a practical way.
Well, I'd like you to refer to the critical metric or output Y that we've defined before, and those other factors that we looked at before when we're trying to look through this hypothesis testing. Now, for any of those factors that have a percentage value, I want you to try to apply the two proportions test. Now, in order to do that, you're going to need to compare at least two different sets of groups for that same factor. Like if you're going to compare that factor across multiple periods of time, or maybe across different locations, or by other types of groups. Also, you can have other factors in the organization that you can use for this exercise if you happen to not have any among those ones you've pre-selected. So before you actually run the two proportions test, ask yourself, do the factors appear to be different? So whatever you're comparing, whether it's across different days, time periods, or across different locations or groups, just looking at the raw numbers, do they appear like there's a difference between them? Would you normally conclude that there's a difference? Then run the two proportions test and ask yourself, are the factors statistically different? And if you have different answers for the two questions, then ask yourself, how does that affect how you typically measure and communicate that difference in the organization? So as an example, does the difference that you might see between how you'd approach this, between the factors, does that affect financial decisions? That is, how people are maybe going to be compensated, or maybe certain process changes, such as how the process may need to be modified, or are there other types of critical actions that could come out of this? If so, if it does make that kind of change, then how should the results from this two proportions test be used to influence your organization? That is, should they change how the factors are going to be compared, like if they want to compare them across different times, locations, or groups? Or should they change how the factor is actually being measured? Or maybe they should change how they react when they compare the metric in this way.
Well, that wraps up this lesson. Check out StatStuff.com for many more resources that can help you achieve powerful results. I'm Matt Hansen. Thanks for watching.